Hi, this is Mrs. Vrobel. This is part one of periodic table and periodic law. So the picture of the man that you see on the right is actually Dmitri Mendeleev. You may have heard of him before. He's probably most known for increasing the elements that they had known at the time in order of atomic mass. And he was really into playing cards a lot. So he was used to shuffling things around and trying to use logic to discern what order the elements should take place. And what he noticed is that because of this order, there was a recurrence of chemical and physical properties. So hopefully you get to see a couple demos of some of those chemical and physical properties in class. Now, he noticed that there were some missing elements if he arranged them in such a way. There were these three elements that didn't quite fit. I'm sorry, four elements that were not even discovered at the time. So he was assuming that they did exist. It was just a question of finding where they might be. But like I said, he arranged them in increasing order of atomic mass. So you notice that as you go from left to right, the atomic masses increase. Now, you may or may not remember from a couple units ago, we talked about periodicity, and actually this system doesn't work. And the reason why is even though we see a reoccurrence of chemical and physical properties, the atomic masses are a problem, especially for certain elements. And you'll see that in a minute when you look at the real or the current periodic table. So the person that we had talked about previously was Moseley. So remember, Moseley had the X-ray diffraction instrument, and he was able to tell, depending on how many protons there were in an electron, he knows that they would increase in their wavelength. So he actually is credited with coming up with periodic law. And he found that the number should take over the mass. The atomic mass works for most of the elements, but not for all of them. And I'll show you some exceptions where the periodicity doesn't work for atomic mass. Okay, so there are 7 periods, and they're essentially going left to right. Then there are columns, which we call families or groups, and you need to know the different families. Notice that the representative elements are the first 2 and the last 6. And when we're talking about that, we're talking about the alkali metals. That's first example of representative elements. And please notice that alkali is going to be different from alkaline, okay? I know that's something that some students have some confusion of. So alkali metals are different from alkaline earth metals. So the first period is alkali, the second period is alkaline earth metals. We skip all of the transition metals and we go into what we call the chalcogens. And they're column 16. So please be careful. There's some older periodic tables, and I'll show you some of the older periodic tables, what they typically do. But if you notice, each column has a number, and we're talking about column 16. Column 17 is a group that you're going to see a lot of chemical reactions with halogens. They're pretty darn reactive, and that's why you'll see a lot of chemical reactions with them. And then the last is noble gases. Now the noble gases, they are not as reactive as maybe the alkali or alkaline earth metals or even the halogens, and that's the reason why they're called noble. So they're pretty much satisfied with the number of electrons that they have, and they don't tend to bond with other elements unless they're perturbed or forced to. So as I mentioned, The group that is not considered representative elements are called transition, and they're essentially the middle block of 10 columns of various metals. And then lastly, there's the intertransitional metals. Those are probably the metals that you're going to see, like the rare earth or the radioactive metals. They are the bottom two rows of the periodic table. So what I would do is I would make flashcards for all of these categories because you're going to need to know them. Okay, so now we need to talk about ions. So ions are a little bit different from atoms. They have an unbalanced charge. They are not neutral. Okay, so whenever we talk about ions, we're talking about a non-neutral element. There's a reason why metals are good conductors of electricity. They tend to give up their electrons readily. They share electrons. They play well with other elements. And the reason why is they don't tightly hold on to their electrons. So the added benefit is we can conduct electricity through them. Because they lose their electrons, please remember that their nucleus is positively charged. So when you lose a negative charge, you end up with a positive charge. So that's why the overall charge will be positive, and we call this cations. Now the way I remember it is that there's a T in the cations, and the T represents the positive charge. You will find that most of the periodic table is cations, and it's essentially the main group of metals that are in the periodic table. Okay, I'm just going to point out a few things for you here on this periodic table. So if you were to look at cobalt and nickel, hold on, I lost my pen there. So carefully look at the masses and notice how we go from 58.9332 to 58.69. So when you're going from cobalt to nickel, you are not seeing an increase in mass. You're seeing an increase in the number of protons, but you're not seeing an increase in the number of neutrons. So there's an exception to Mendeleev's periodic table. Another one I'll point out here is seborgium, which is a 263, and borium is a 262. So here we see an increase in protons, but we don't see an increase in neutrons. Okay, so that's where Mendeleev's table does not fulfill itself. And then lastly, we have plutonium and americium. Remember, americium is from your smoke detectors. We go from a 244 to a 243. So we see an increase in protons. And that's where we don't see Mendeleev's table following according to masses. Just to let you know, here's the numbers that I was talking about for each of the columns. So 1 through 18. It used to be, the way I learned it, there were these Roman numerals on top. Okay, they've gotten away from it. The older periodic tables don't have this. So you typically just see the numbers 1 through 18. Okay, let's talk about nonmetals. So nonmetals are in that hot corner on the right-hand side of the periodic table. We talked about before the fact that they are insulators. So because they're insulators, they don't like to share their electrons very well. They tend to hold on to them very tightly, so they're completely opposite of the metals. Because they like their electrons, remember the nucleus is positively charged, but if you have an excess of electrons, you're going to have an overall negative charge, and because of that, they are called anions. So what I think of is this N here as a symbol for negative, where I say a negative ion, so a negative ion, and that tells me it's negatively charged. Okay, when you're looking at naming these ions, you typically call them IDE. So for instance, fluorine, when it becomes an ion, you don't call it fluorine, you call it fluoride. Okay? Same with chlorine. If chlorine becomes an ion, you don't call it chlorine, you call it chloride. So it ends up having an IDE ending. Okay, here we go. So when we're talking about chemical properties of the elements, please remember that the atomic number, not the atomic mass, is the identity of the element. So whatever the atomic number is, that tells you it's that type of element. When we're looking at electrons, so electrons actually help determine the chemical properties. So electrons are what help us actually form chemical bonds with other electrons. Metals tend to form cations, nonmetals tend to form anions.